Okay, can you write that down? Single and double support. Not too much in this first lesson, so we'll definitely get 2 topics done this morning. Yeah. You got that? Yep. So, what would happen if equal but opposite forces are applied at the ends? If I put one force up and the other force down, what would happen? Yeah, what do you think, Bello? Yeah. Yeah, so what would happen to the plank? It would what? You said it, yeah. You see, I think some of you are getting the idea. If you have something like this, we've seen it before. Force up, force down. It actually will rotate. But if we try to use Newton's law, let me call that F1 F1 or something. Newton says F would equal F1 minus F1, which is 0. And that's kind of a problem, because that's not quite right, because that makes us think 0 equals MA, and that makes us think A is 0. And we might think it's not moving, or not accelerating at least. So, it would seem like the plank shouldn't move, but obviously it does. So what gives? The plank is moving, it's rotating. So far we've only looked at 2 types of motion. We've only looked at horizontal motion or vertical motion. We've not looked at rotation. Do you understand? So this is actually a 3rd dimension, nearly. You have an X, we had a Y, and now we have this dimension. So when we're talking about X, we say positive, negative. We're talking about Y, we say positive, negative. And when we're talking about rotation, what do we say? Clockwise and anti-clockwise. So a turning force is making it turn. If it's not turning, then it would be in equilibrium. So to be precise, when we say equilibrium, we mean the following. An object is in equilibrium if the total net force and the turning force is 0. Meaning, force to the left equals force to the right. What do you think I'm going to say next? And what will I say lastly? No. Up, down, down, left, right, A, B. No. What's the last one? And the clockwise will equal the anti-clockwise. So, I need you to write this box down. This is the definition of equilibrium. You okay, Ming? Do you know this word equilibrium? It's like it means balanced, not moving. Steady. No, if it's turning, it's not in equilibrium. Yeah, but what did I just say here? I said not only do the ups have to equal the down, but also you need this. Have you got that? No. Not yet? Yeah? Continue? Yeah? Okay. The last point, this last point here, is actually known as the name of the lesson. This is called the principle of moments. I think it's worth noting that. So if you want, beside this one, you can say in brackets here, principle of moments. Yeah? Have some of you seen this before? Maybe. Okay, continue? Yeah? Its principle of moments is the total clockwise moment equals the total clockwise, anti-clockwise moment if it's in equilibrium. Let's have a look at a simple example. A 40-kilogram boy sits at the end of a 100-kilogram seesaw, and his sister of 30 kilograms sits at the other end. The pivot is in the center of the 5-meter seesaw. The seesaw is not balanced, and so it rotates. So originally the picture is like this. Whoops, what's going on here? Sorry, just a sec. Okay, so originally the picture is like this. You have the seesaw. You have it here. You have the boy here. You have the girl here. And, whoops, a daisy. What did we say the boy's mass was? 40. So what's his weight? Well, 40 g. And what's the girl's weight? What's hers? No, the girl is not 100 kilograms. 30 kilograms. Okay. And the seesaw is what weight? 100 kilograms. Okay. And the reaction is going to balance here with the seesaw. Yeah. So these two here actually cancel, really. Okay. But is the seesaw in equilibrium? No. It is going to do what? Rotate. Will it rotate clockwise or anti-clockwise? Anti-clockwise. Because the boy's side is heavier, this is going to push down and this is going to push up. So it's rotating around like that. This is called clockwise. You confused me now. This is called anti-clockwise.
So is the boy 40 grams or 40 kilograms?
Now, you know the answer to that. How many boys do you know have a mass of 40 grams? No, how many boys have a mass of 40 grams? And 40 grams would be lighter than my cup of coffee. How many boys? No, so it's obviously not 40 grams, it's 40 G. G is 9.81. Okay. Right. So just to be clear, the girl is not 100 kilograms and the boy is not 40 grams. Okay, these are normal human children. All right. Okay, continue. So what the father decides to do is he moves the pivot here to balance the seesaw. Will he need to move it to the left or will he need to move it to the right? He will need to move it to the left, won't he? And our job is to calculate where that point will be. So I'll redraw the picture now. This is what the picture will now look like. The pivot will be somewhere on the left. We don't know where. Let's draw the forces. Here we have 40 G, not grams. And here we have 30 G. And here, what have we got? 100 G. And here, what have we got? What force is here? Reaction. Now, we know some distances. We know the distance from here to here. No, read it carefully. Yeah, very good. 2.5. Okay? So the father has to move it from the center to the left. Let's call that distance he moves it, we'll call it x. So, what must this distance here be? 2.5 minus x. We are trying to solve for x. Now, in fact, we can quickly, very quickly get the or. Watch. Which rule here is useful for calculating the or? The second. No, the second can give us the or quickly. What is the total force down? 170 G. Therefore, what must the total force up be? 170 G. What is the total force up in this picture? It's or. So, this or here, it has to be what? It has to be 170 G. Right? Tell me, if it wasn't 170 G, suppose it was 171, what would be happening? Where's my pen gone? Yes. Hang on. And if it was less than 170 G, what would be happening? The seesaw would be going down. Yeah. Oh, come on. Come on. What's gone wrong? Pen. 170 G. Question?
Yeah, so in the last diagram, the 32,
Sorry, do I have my numbers wrong? 40 and 30.
no,
Oh, my first picture's wrong? Oh, sorry. Yeah, my brain was doing two things at once. I was saying 100 kilograms and the mass is 100 G, and the weight is 100 G, and they crashed together in my brain.
So it's 100 kilograms.
Yeah. Okay. You could have said that sooner.
That's why he asked 30 G. And you were asking which one.
Yeah, but my point still stands. There's not many people who are 30 grams. Yeah. I know what confused me. Somebody said 100 kilograms, and that's what confused me. Now, I'll leave him alone. He's normally very helpful to me, so it's fine. It's fine. Right. So, what will we do next to help us calculate the x? The moments. Right. So, where is the turning point here? Where is the pivot? Where's the turning point? Correct. Yeah. Right here, isn't it? Right. Now, please be very careful. Tell me, this force here, compared to the pivot, will this force make it turn clockwise or anti-clockwise? Very good. I'll write an A here for anti. Now, this force here, compared to the pivot, will it make it turn clockwise or anti-clockwise? Very good, clockwise. And this force here, will it make it turn clockwise or anti-clockwise? Clockwise. And what about this force here? Correct. No effect. Why? Yeah, it's passing through the turning point. Right. So, let's use our formula. T anti-clockwise equals turning force clockwise. So, the first one would be 40 G times the distance. What's the distance? And that should equal what?
The 30.
Well, let's start with the 100. 100g times x plus 30g times... No, just 2... oh, yes, thank you. 2.5 plus x, because it's from here, isn't it? Thank you. Okay, what is in common to these three terms that I can cancel?
G.
The g. No, not quite. So now I have 40 times 2.5. What's that? 100? Minus 40x equals 100x plus 75 plus 30x. Do I have that right? Looks okay? Yeah? Okay. So how many x's have I got? 170, is it? X equals 25. Isn't that right? So, what is my x? What is it? 0.147. So, he moves it 14.7 centimeters to the boy, to the left. We'll say to the boy because it's clearer. Not too difficult. Question? What? Repeat? No. I went so slowly through this. I mean...
What's the 100g come from?
No. I'll do another example, but I can't repeat this. I'm already 2 hours behind because of the tutorials. Yes?
Where is the 100g come from?
That's the weight of the seesaw.
Oh, yeah. The seesaw has a weight.
Oh, definitely.
But not all cases.
In the exam, they usually have you use a weight of the object. In other words, Bello, they don't simplify it and say ignore the weight of the seesaw.
Okay, but then to know the clockwise or anti-clockwise direction, that's what confuses me.
That's what confuses everyone. But you got the right answers, though. Didn't you tell me these? Oh, you did? Okay. Well, tell me, Bello. Imagine that this is a clock hand, like an hour hand. And if you hang a weight at the end of the hour hand here, like what time is this hour hand pointing to? What number? 9. So, if you hang a weight here, would you make the clock run forwards or backwards? Yeah, anti-clockwise. Now, if this is the hour hand, what time is it pointing at? 3. If you hang weights while it's in the 3 o'clock position, what way will you make the clock run? Forwards or backwards? Forwards, so there you go. That's how I worked out anti or clockwise. Yeah. You know, like just a visualization of, we use the language clockwise and anti-clockwise because we imagine a clock. So we imagine the clock hand being at 3 o'clock and hang weights on it. We'd make the clock run forwards clockwise.
When you hang the weights like on the tree hand, how would you hang the weights for it to go?
You can't. You would have to be pushing up while in 3 o'clock position to make it run backwards. Yeah. Okay, please write that down carefully and we'll do more examples. Did you write it down? Did you write it down? I can continue? Marwan? Okay. You have this written down, Ethan? Okay. How much have you left to write down, Marwan? Okay. Go. Yes? Okay. Right. Next, we'll do another example. A 100-gram meter stick is suspended by two strings. The first string is tied at the 25 centimeter mark, and the second string is tied at the 90 centimeter mark. What are the tensions in the string? So let me draw this. You know what a meter stick is? How long is it? 1 meter, yeah. 1 meter, which is also 100 centimeters. Now, at the 25 centimeter mark, you have a string. And where else? At the 90 centimeter mark, you have another string. Also, there's one more force. What is the last force? The weight. What is the weight of the meter stick? What's the mass of the meter stick? 100 grams, which is how many kilograms? 0.1. So what is the weight? 0.1 g. Okay. Now, this force I'll call T, and this one here I'll call S, and our job is to find T and S. Right. What is the first equation I can make? The up force equals the down force. So what could I say here? T plus S equals 0.1 g, which is 0.981. Now, what type of problem is this going to become in a moment? Simultaneous, isn't it? Yeah? So I need to make a second equation. So how can I make the second equation? Yeah, using the turning forces. Okay? So, could someone wake Tommy up? It looks like he's dozed off there. You doing okay, Tommy? Yeah, okay. Right. We use turning force. So my next question is, where is the turning point? Where is the pivot? You're going with here. Okay? Any other suggestions? Where? You're going with here. Any other suggestions? Yeah, why not? Here. Anything else? We have that. Where else? Yeah, what? Here maybe? Could be here. Maybe it's here. Yeah. Oh, it's in the middle somewhere, like here. 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 Okay, I'm annoying you guys now because the answer is technically you're allowed to put the turning point anywhere on the diagram. You'll get the same answer, which might seem a little bit strange, especially considering the last example we did. It seemed so obvious that this was the turning point, right? But believe it or not, if you were to redo the calculations with the turning point here, which obviously seems wrong, you would get still the right answer. Why is that? Well, it's because the system is in equilibrium. When it's in equilibrium, it's not really turning, is it? So, in fact, you can say the turning point is anywhere. Now, if that's confusing you, it doesn't matter. The moral is, the point is, you can put the turning point anywhere. So just put it wherever you feel would make you happiest. Okay? So, your first instinct, Abdul Rahman, was to put the turning point here in the center, like with the seesaw. If you want to do that, that's fine. I won't, though. I'm going to put the turning point somewhere more convenient. I'm going to put it here. And you'll see in a moment why I choose this as the turning point. What would it do? Yeah, an easier equation. If this is the turning point, is this a clockwise or an anti-clockwise force? Clockwise. And this one here? Anti. And this one here? No effect. No effect. No effect. So, what is the distance from here to here? 0.25 0.25. Because remember, this is in the center of the meter stick. Yeah? And we times that by 0.981. And that should equal, what is the distance from here to here now? Well, that's between 25 and 90. So what's that, 65? Yeah? 0.65 times S. S, yes? Yes? S is the force, isn't it? Now, why is this second equation nice? No, you have 1. It can easily give you what? You can very easily get S. You just have to divide by 0.65. So can someone tell me what the S is from this? Newtons. And if you know the S, then that means you can, yeah? Substitute in and easily get the T now. What's that? .604, is it? Newtons.
So 25 and 90 meters, is that the distance from the left?
Yeah, because it's the numbers on the meter stick.
Okay, so I have a question.
Yeah.
Everywhere the turning point is the action. Is that where the action is?
Are you asking me about what? The turning point?
Yeah, like where you put the turning
Yeah.
point.
I chose to put it at the T.
Yeah.
Yeah.
You made that place the action, which means
I made it the pivot. This is the center of the turning, yeah. But remember, Bello, you're free to put the turning point anywhere on the diagram if it's in equilibrium.
That means we don't need the first equation. Make the second equation like twice.
With the
Yes.
turning point.
Yes, you could make 2 turning point equations. Yeah, it's fine, no problem. Now, when you look at what I wrote, did I really do a lot here on the screen? No, and this in the exam would be a section A question. How many marks? 4 usually, yeah. Because it'll be 1 mark for the first equation, 1 mark for the second equation, 1 mark for the right T answer, and 1 mark for the right S answer. How many students do you think fully get this right? Surprisingly, not many. This is one of the 2 topics that students seem to screw up in the exam. The first topic is projectiles, and the second topic is turning forces. I can understand why people screw up projectiles. It's hard. Don't understand why people screw this up in the exam. It's easy. So, my theory is students have trouble with clockwise and anti-clockwise because they're so used to having digital watches that they don't fully understand what clockwise and anti-clockwise mean. Yeah, I know. Yeah, true, yeah. Yeah. Still, people mess it up in the exam. So, I don't understand. I don't understand. They just do. Okay. Continue? Yeah? Okay. Yeah, I don't think I need to do another example. This one is exactly the same. Yeah, this one's exactly the same. So, whoa. What I'd like to do is go on to the next lesson quite soon, because you remember I said we're a little bit behind due to homeworks. So, what we'll do is I'll give you, maximum 10 minutes to practice these questions, and then we'll start the next lesson. Now you can see they're not that difficult, and I think they're quite common in the exam. How many questions do you have there on the database? Is it a lot? 12 or so, maybe? 13, is it? Yeah? Okay. Right. So, can you try these for about 10 minutes? Yes, 10 minutes, and then we'll start the next lesson.